And welcome to Chapter 13, States of Matter. Hey, in Chapter 2, if you recall, we were, part of Chapter 2, we talked about the different states of matter, solids, liquids, and gases. We gave you a few properties concerning solids, liquids, and gases, but we never really explained why substances are in a particular state of matter. Why are they a solid? Why are they a liquid? Why are they a gas? Well, in this chapter, that's what we're going to try to unpack. We're going to try to figure out why different states of matter exist. And we're going to start off by talking about gases in 13.1. Let me get my pen ready here. It looks like we're ready to go. In 13.1, the nature of gases, the first thing we want to talk about is kinetic theory and the model for gases. Now, you may have heard of the term kinetic before, usually in terms of kinetic energy. If you recall, maybe from middle school, kinetic energy is simply the energy of motion. The energy of motion. Now, there's an equation that expresses kinetic energy. You may have seen this before. This is Ke as kinetic energy. Ke equals 1/2 mv squared, where m is the mass and v is the velocity. Now, if you notice, kinetic energy is related to the square of the velocity, meaning that this is going to be an exponential relationship. If you look at different mathematical relationships, and we went over this a little bit in the opening chapters, if you plot different relationships, you can have linear relationships, which are straight lines. You can have inverse relationships, which are downward curves, meaning that as one increases, the other decreases. And you can also have exponential relationships, whereas one increases, the other one really increases, and you get this upward curve. This is the type of relationship that kinetic energy is. When you plot kinetic energy, Ke, versus the velocity, v. Alright? Kinetic deals with motion, and when you increase the speed, the energy is going to be increasing. But if you double the speed, it doesn't mean you're doubling the energy. You would actually quadruple the energy. Car crashes are a good example. A car crash at 20 miles an hour is one thing. A car crash at 40 miles an hour is not twice as hard. It's actually 4 times the amount of energy involved with that particular reaction or that particular crash. All right. So that's what the term kinetic means, and it means motion. And it is an exponential relationship. Now, the theory that describes why gases behave, and in fact this also describes why all states of matter behave the way they do, is called kinetic theory, or oftentimes is called kinetic molecular theory. Kinetic meaning motion, and obviously molecular dealing with things at the molecular level, so it's the motion of molecules theory. So let's unpack what this theory is. Now remember, a theory or a model is a set of assumptions that describe how or why something occurs. So we're going to go through a set of assumptions that explains why gases behave the way they do, and then we'll transfer that to the other states of matter. Alright, so scrolling down here. Okay, kinetic theory. In our textbook, it divides it out into 4 main points, although other textbooks will divide it into different numbers of points. The first point that Mr. Waterman makes is that particles of a gas are considered to be small, hard spheres. So particles of a gas are small, hard spheres, and they have an insignificant volume. Now, when we mean insignificant, the volume is there, but we don't have to be concerned about it. For example, if you have a container, let's draw our little container off to the side here. We'll put a lid on it because that way the gases cannot escape. You might have a particle here and here and here and over here and over here, but these particles are so small that when you add them up, you wouldn't even notice them taking up any space in this box. If this box is a 2-liter container, if you add up all the particles, the empty volume in there is still considered to be 2 liters. As opposed to if you had huge spheres, they would actually take up some room and you would have to subtract that out from the box if it was filled up with, say, rocks. But in this case, these things are so small, we don't even have to worry about it. Number 2, the motion of the particles in a gas is rapid, constant, and random. Motion is rapid, constant, and random. So these particles inside this box are just bouncing all over the place. Here, this could be going in this direction, this could be going in that direction, this could be going in that direction, this could be crossing its path and going in that direction. So it's going very fast all the time, and you can't necessarily predict where every particle is going at any given point. Next, all collisions are perfectly elastic. All collisions are perfectly elastic, meaning that they won't slow each other down. As opposed to an inelastic collision, say if you go shoot some pool. Now, first of all, the balls will be slowing down on the table because of the friction between the balls and the felt on the table. But if you bounce a pool ball off the cushion, it often slows down. It deadens because the collision between the ball and the bumper actually absorbs some energy and transfers it to the table, so the balls tend to slow down. All right. That's not the case when these particles inside of our box over here, if they collide with one another, they don't slow down. They just keep going at the same with the same total energy as they had before. Now, one might speed the other one up, and the other one would slow down. So I guess that's a little bit of a misnomer. We should say, and then we even cross this out, no loss of energy. Because one particle can slow down, but the other one would speed up. And there would be a complete transfer of energy or conservation of energy. Okay, next. In the fourth part of this, well, you know what? Mr. Waterman doesn't even break this up into 4 parts. I think what I did is I put the insignificant volumes portion in with number 1 there. I'm going to write that down here again because that's very important. Insignificant volume. Typically, a book is going to separate that one out because it turns out that that's not actually correct. All theories have some type of limitation to them, and so when we say that these particles have an insignificant volume, is that absolutely true? No, it's actually not completely true. Are all collisions perfectly elastic? No, that's not actually true, but it helps simplify things so that we can make some good predictions. And as we go and talk about why gases behave the way they do, particularly in Chapter 14, then all of these things I think will come to light. Okay? In the next podcast, we're going to introduce you to the idea of pressure.